What if the feeling you've had in the quietest moments of your life, the sense that something about reality isn't quite right, isn't just imagination, but the beginning of a question science itself cannot fully answer? Not a casual curiosity, not a late-night thought experiment, but a deep, persistent unease that the world you move through every day might have a hidden layer beneath it. A structure behind the surface. A set of rules that feel too precise, too consistent, too deliberate to be random. If you've ever felt that, even for a second, then you're already standing at the edge of one of the most unsettling questions we can ask. Is this reality truly real, or is it something constructed? I want you to sit with that not as philosophy, not as entertainment, but as a genuine possibility, because I've felt it too. And that matters, because I'm not someone who is trained to trust feelings like that. I'm a physicist. My entire life has been built on equations, on evidence, on the discipline of following logic wherever it leads. I'm supposed to rely on what can be measured, tested, proven, and I still do. But there's something I need to be honest about, something that doesn't always get said out loud in scientific circles. When it comes to the question of whether the universe might be a simulation, the answer is not as simple as people expect. It doesn't close neatly. It doesn't resolve into certainty. If anything, the deeper you go, the more it opens into something far stranger. So, instead of dismissing it, let's examine it carefully. Because this idea, the simulation hypothesis, is not just science fiction. In its modern form, it's actually a logical argument. It says this: if it's possible to simulate conscious beings in a reality that feels completely real to them, and if advanced civilizations have both the ability and the reason to run these simulations, and if they can run many of them, then statistically, it's far more likely that any given conscious being like you is inside a simulation rather than in a base reality. That idea was formally developed about 2 decades ago, but its roots go much deeper. Across history, across cultures, people have questioned whether reality is truly what it seems. From ancient philosophical traditions to modern stories, the same intuition keeps appearing, that what we experience might be a projection of something more fundamental. But instead of repeating those familiar ideas, I want to take you somewhere more grounded into what physics itself actually tells us. Because here's where it gets interesting. At the most fundamental level, the universe doesn't behave the way you might expect. It doesn't flow smoothly and continuously. Instead, it comes in discrete pieces. Energy is quantized. Motion is quantized. Even the smallest measurable unit of action sets a hard limit on how finely reality can be divided. And when we reach the smallest scales we can currently describe, our theories stop working altogether. Space and time themselves may not be continuous. They may have a minimum size, like pixels in an image. Now, that doesn't prove we're in a simulation, but it's exactly what you would expect if reality were computational. A system with a smallest unit, a resolution limit, a structure built from discrete steps rather than smooth continuity. It doesn't confirm the idea, but it keeps it firmly on the table. And there's more. The deeper we go into physics, the less we find things and the more we find patterns, relationships, information. The universe doesn't just use mathematics to describe itself. It seems to be mathematical at its core. Not matter in the classical sense, but structured information behaving according to precise rules, almost like a system running code. Even more striking is the realization that information itself has physical consequences. Erasing a bit of information produces heat. The entropy of a black hole depends on its surface area, not its volume. This suggests something extraordinary, that everything happening in 3 dimensions might be fully described by information stored on a 2-dimensional boundary. If that sounds familiar, it should, because if you were designing a highly efficient simulation, that's exactly how you might build it. And that brings us to a deeply unsettling idea, one that changes how we think about reality itself. Not by proving anything outright, but by making it impossible to ignore the question any longer. Because once you see how closely the structure of the universe aligns with the logic of computation, you can't simply go back to assuming everything is exactly as it appears. And once you accept that the structure of reality could be computational, the next step is where things become far more difficult, because now you have to ask a question that doesn't just challenge physics, it challenges the limits of knowledge itself. If this is a simulation, where is it running? What is it running on? And most importantly, could we ever actually know? At first, it feels like a straightforward extension of the idea. If there's a simulation, then there must be a system behind it, a deeper layer of reality, a kind of hardware supporting everything we experience. That's the assumption most people make. But here's where the logic begins to break down. Because if the universe we observe is perfectly consistent, if every law holds, if every measurement aligns, if the mathematics never contradicts itself then from the inside, there is no experiment that can reveal the outside. Think about that carefully. No matter how advanced our technology becomes, no matter how precise our instruments are, every observation we make is still part of the system itself. Every test we design is governed by the same rules we're trying to question. So even if there is a deeper layer, a substrate beyond this reality, we have no direct access to it. And that means something very uncomfortable. The question of whether we are in a simulation may not just be unanswered, it may be unanswerable. Not because it's meaningless, but because it lies beyond the reach of empirical science. Physics depends on observation, measurement, verification, but this question sits outside all three. It's not that we haven't figured it out yet, it's that the tools we use to figure things out may never be able to touch it. This is where physics and philosophy collide in a way that neither field finds entirely comfortable, because now we're no longer asking how reality behaves, we're asking what it is. And more importantly, what it means to even ask that question. I've spent decades working under the assumption that reality can be understood, that if we push hard enough, think clearly enough, build the right mathematical models, the universe will reveal its structure. And in many ways, that belief has been justified. We've uncovered laws that describe everything from subatomic particles to the expansion of galaxies. But alongside those discoveries, something else has become clear. There are boundaries. Not temporary ones, but fundamental limits to what can be known from within the system itself. And the simulation question sits right on that boundary. So the honest answer, the only answer I can give without pretending certainty, is this: I don't know, and neither does anyone else. It may be a permanent unknown, a question that can be asked, explored, even partially understood, but never definitively resolved. And that realization can feel unsettling, because we're not used to carrying questions that don't have answers. We want closure. We want certainty. But here, there is none. Only the awareness that we are inside something whose deepest foundation may always remain hidden. But here's where everything takes an unexpected turn, because when you really sit with this uncertainty, when you stop trying to force an answer, you begin to notice something surprising. The simulation question doesn't lead to meaninglessness. It doesn't strip reality of value. In fact, it does the opposite. Because regardless of what this universe ultimately is, your experience inside it is undeniably real. The emotions you feel, the connections you form, the moments that shape your life, those aren't abstract. They're lived. They're felt. They have weight. If this is a simulation, then it's one that is actively running. Time is genuinely passing within it. Pain is genuinely experienced. Joy is genuinely felt. Relationships are genuinely formed. Whatever the underlying mechanism may be, the experience itself is not an illusion in any meaningful sense. It's your reality. And that changes the focus of the question entirely, because instead of asking, is this real, the more important question becomes, what do I do with it? How do you live in a reality whose ultimate nature you cannot verify? How do you decide what matters when the foundation itself is uncertain? These aren't physics questions anymore. They're human questions. And they don't go away just because we understand more about the universe. If anything, they become more urgent. Because when you spend your life studying reality at its deepest levels, you start to notice something about your own way of living. There's a tendency to prioritize abstraction, to treat equations as more solid than emotions, theories as more reliable than experiences. In science, that approach works. It's necessary, but outside the lab, it can quietly distort how you engage with life itself. Because the people in your life are not variables, they're not interchangeable, they're specific, unique, and irreplaceable. And no equation can fully capture that. And yet, it's easy to fall into the habit of treating the abstract as more important than the immediate, to let ideas matter more than moments, to stay mentally somewhere else while life is happening right in front of you. And that brings us to something physics itself struggles to explain a problem that might sound technical at first, but carries a deeply human meaning when you look at it closely. It's called the measurement problem in quantum mechanics. At the quantum level, systems exist in multiple possible states at once, a superposition. But the moment you measure them, they collapse into a single, definite state. The question is, what causes that collapse? No one fully knows. But think about how that idea translates into everyday life. Because in a very real sense, we move through our lives in a kind of mental superposition, our attention split across past, future distractions, obligations. We're present, but not fully. Here, but also somewhere else. And then there are rare moments, moments of true presence when everything collapses into clarity. When you are fully there, fully engaged, fully aware of what's happening right now. That's where life actually happens. And if the nature of reality itself is uncertain, if the foundation beneath everything might never be fully known, then those moments of presence become even more important. Because they are the only place where anything is truly experienced. So, as we move forward, the question is no longer just about the universe. It's about you, your attention, your choices, your way of being inside this reality, whatever it ultimately turns out to be. And in the next part, we're going to go even deeper into that connection, into how time, focus, and the way you live your life might be shaped by the very same principles that govern the universe itself. If you keep following this line of thought, something unexpected happens. The discussion stops being about distant cosmology or abstract philosophy and starts turning inward. Because once you accept that reality may be fundamentally structured, maybe even computational, the real question becomes how that structure shapes the way your own life unfolds inside it. To understand this, it helps to look at something physics already tells us very clearly. Time is not experienced equally everywhere. In Einstein's theory of general relativity, time is not a universal constant ticking the same for everyone. It bends. It stretches. It slows down depending on gravity and motion. The stronger the gravitational field, the slower time moves relative to somewhere with weaker gravity. This isn't theoretical speculation. It has been measured. It has been tested. It is part of how GPS systems correct their signals every single day. Now think about what that actually means in a more human sense. It means that time is not something you simply move through at a fixed rate. Your experience of it depends entirely on your environment, your state, and your conditions. In strong gravitational fields, time literally passes differently. And that opens a strange analogy when you look at human attention. Because attention behaves a little like gravity. When something fully captures your mind, a problem, a passion, a fear, a goal, it begins to warp your subjective experience of time. Hours compress or expand. Entire days can pass unnoticed. Or a single moment can feel stretched and dense with detail. Your internal clock is no longer synchronized with everything around you. It bends around what you are focused on. In physics, we call this time dilation. In life, we often just call it being absorbed. But the effect is surprisingly similar. The stronger the gravitational pull of your attention, the more your experience of time deviates from the outside world. And that leads to something important. When your attention is strongly captured by one domain work, thought, obsession, or analysis, everything outside that domain continues at full speed. Life doesn't pause. Relationships don't wait. Moments don't freeze. They move forward at their normal rate while your subjective experience slows or narrows around the focus point. You don't feel the full passage of time elsewhere, but it still passes. And that creates a kind of mismatch. Not immediately, not visibly, but over time, the accumulated difference becomes real. Conversations that weren't had, moments that were postponed. Experiences that were deferred because attention was somewhere else. Then, eventually, you re-enter a broader frame. You look up, and you realize time outside your focus didn't slow down with you. It continued without interruption. This isn't a moral judgment. It's just a structural feature of how attention and time interact in conscious experience. But it becomes important when you start thinking seriously about how life is actually lived inside the constraints of physics. Because here's the key point. You only ever experience one moment at a time. Even if reality is vast, even if the universe is computational, even if everything is structured in ways we don't yet fully understand, your access to it is always local, always now, always this moment, unfolding in sequence with the next. Which means something subtle but crucial. The only place life ever actually happens is in the present. Not in the abstract future you plan for, not in the remembered past you reconstruct, but in the immediate experience of attention as it lands somewhere, fully or partially. And that brings us back to quantum mechanics in a way that is more than metaphor. In quantum theory, systems exist in multiple possible states until they are measured. Before measurement, they are described by probabilities, by overlapping possibilities. Only when an interaction occurs does the system settle into a definite outcome. That transition from possibility to actuality is one of the deepest unresolved questions in physics. But if you translate that idea carefully into lived experience, something interesting appears. Your attention behaves in a similar way. At any moment, your mind holds multiple possible directions. What you could focus on, what you could think about, what you could respond to. But only one of those possibilities becomes your actual lived experience. The rest remain unrealized. And the act of full attention, true presence, is the moment where that ambiguity collapses into a single, concrete experience. Not in a mystical sense, in a structural one. You stop being distributed across possibilities. You become situated in one reality, one moment, one interaction. And that is the only place where experience actually exists. This is where the physics stops being abstract and starts becoming strangely personal. Because it suggests something simple but often overlooked. The quality of your life is not determined by the total amount of possibilities available to you, but by the degree to which you actually inhabit the one you are in. And most of us, most of the time, don't fully inhabit it. We drift, we anticipate, we recall. We divide attention across timelines that don't actually exist in the present moment. And in doing so, we live in a kind of continuous partial state, neither fully here nor fully elsewhere. This isn't a failure. It's just how cognition works. But it does mean that presence is not automatic. It's something that has to be actively chosen again and again, moment by moment. And if there is any lesson from physics that translates cleanly into human experience, it might be this. Structure determines experience, but attention determines where within that structure you actually live. The universe may be governed by mathematical laws we barely understand. Reality may be computational, layered, or something even stranger. But none of that changes the fact that your experience of it is local, immediate, and singular. Which means the question is no longer just what reality is made of. It becomes, how are you moving through it? Because while the universe may contain vast structures, your life is always happening at a single point inside it. And what you do with that point, what you allow yourself to notice, to engage with, to fully enter, is where everything you call meaning actually forms. In the next part, we'll go deeper into what that means, when applied not just to attention, but to memory, identity, and the strange way we experience ourselves as continuous beings inside a universe that may not be as continuous as it feels. What we arrive at next is a point where physics itself becomes uncomfortable, not because it fails, but because it works too well inside its own boundary. If reality is fundamentally built from information, and if that information is structured in a way that behaves like a rule-based system, then a natural question appears. Can we ever step outside that system to test what is beyond it? The honest answer, based on everything we know about science, is no. Not in any direct way. Every experiment we can perform, every measurement we can design, every observation we can make is already inside the rules of the universe we are trying to understand. We cannot access a position outside those rules to compare against them, because there is no known physical mechanism that allows an observer to leave the system and still perform measurements on it. That limitation is not a failure of technology. It is a structural constraint on what it means to do science from within a universe. This is where the simulation discussion becomes technically precise in a way that is often missed in popular interpretations. If a universe is perfectly self-consistent, meaning its laws are internally coherent, stable, and complete from the perspective of its inhabitants, then any observer inside it will always interpret those laws as fundamental. There is no internal signature that reliably distinguishes base reality from a perfectly constructed simulated reality. This is not a loophole. It is a consequence of logic. If every possible observation is generated by the same rule set, then no observation can step outside that rule set to verify its origin. In that sense, the simulation hypothesis is not something physics can confirm or reject. It is something that sits at the edge of what physics is capable of addressing. And this is where things become more subtle than most discussions allow. Because at this point, the question is no longer, is this real or not real? The question becomes, what does real even mean if all accessible evidence is produced from within the same closed system? From a physical standpoint, reality is defined operationally. If something produces consistent effects, if it follows predictable laws, if it interacts causally with everything else in the system, then it is treated as real. Physics does not require an external justification for existence. It only requires internal consistency and reproducibility. So even if one were to imagine an external generator of this universe, that assumption does not change the way anything behaves inside it. The equations remain the same. The predictions remain the same. The experience of time, matter, energy, and consciousness remains unchanged. Nothing about daily existence becomes different in any measurable way. This is why many physicists become cautious about assigning too much weight to the simulation framing. Not because it is impossible, but because it does not currently alter the predictive structure of the theories we use. It is, in a strict sense, empirically inert. However, that does not make it meaningless. What it does is shift the focus away from origin and towards structure. Instead of asking where reality comes from, we are forced to ask how reality behaves from the inside and why it behaves with such extraordinary mathematical coherence. That question remains one of the deepest open problems in physics. There is also a psychological layer that cannot be ignored here. Humans have always searched for a higher-level explanation of existence. In earlier eras, this took the form of cosmologies, metaphysical hierarchies, or divine frameworks. In the modern scientific era, the language has changed, but the instinct remains. The simulation hypothesis is, in part, a modern expression of that same drive to locate reality in a deeper explanatory layer. But physics, at its most disciplined, resists that impulse unless it is supported by testable consequences. And so far, no version of the simulation idea has produced a unique, observable prediction that would clearly separate it from a non-simulated universe governed by the same mathematical laws. This is the point where careful reasoning matters most. It is easy to turn uncertainty into narrative. It is easy to take gaps in knowledge and fill them with imagined structures. But the scientific position remains deliberately restrained. If two explanations produce identical observations, then science treats them as operationally equivalent until a difference can be measured. So we remain in a strange position. We have a universe that looks informational at its foundation, governed by deep mathematical consistency, possibly discrete at its smallest scales, and holographically encoded at its boundaries. But none of that tells us whether there is an external computer or whether the structure is simply what reality is. And that is where the physics ends its authority and something else begins, not speculation, not mysticism, but interpretation. A recognition that understanding the structure of reality does not automatically grant access to its ultimate origin. What remains, then, is not an answer, but a boundary. A clear line between what can be known from inside the system and what may forever remain outside it. And it is at that boundary that the next part of the discussion begins to shift away from cosmology and towards something far more immediate. What it means for a conscious mind to exist entirely within that structure, regardless of what lies beyond it.